Here we're going to practice starting to plot some polar curves. And the first thing I want to say right from the get-go is polar curves are still plotted on the XY plane. So, we're going to slowly lead into this idea of how to plot polar curves, but remember, whenever we plot anything, we can always make a table of values. And actually, we're going to do the same thing here. So for polar curves, we're typically given that the polar radius r is a function of the angle theta. And when we go ahead and begin to plot these, I want us to notice that, well, if we're plotting polar curves, again, we're on the XY plane, we're really asking ourselves at a particular angle, say theta equals pi over 6. We're asking ourselves, how far do we go out for r when theta equals pi over 6? When theta equals pi over 2, we're asking ourselves again, how far do we go out along that direction of pi over 2 for our polar radius? When theta is something like, say, 3 pi over 4. We're asking ourselves again, well, the angle is 3 pi over 4. How far out from the origin do we have to go for that polar radius? So at every single angle around the XY plane, we're really asking ourselves, how far along each angle do we go out? And that is what the distance r represents. So, if we are given a function r that's a function of the angle theta, we can again begin to make a table and plot all of those values. So we can, of course, make a column of theta values and then make a column of r values, since r is a function of theta. And then we just notice, okay, at a particular angle theta, we have a particular distance from the origin that we're moving along. So we can, of course, make these tables in the same way we made tables for functions, y is a function of x, or for parametric curves, where x and y coordinates were both functions of parameters, such as t. Here we can do the same thing. Ask when the angle is 0. So the angle is 0. We are right along the x-axis. How far along the x-axis do we need to move at an angle of 0? When we're at an angle of pi over 4, how far along that angle of pi over 4 do we have to move for our r? When we're at an angle of pi over 2, we're asking ourselves, well, at an angle of pi over 2, which is straight up, how far along that angle of pi over 2 do we need to move from the origin? So again, I'm really trying to emphasize this idea of at a particular angle, we're really asking ourselves, how far along in that particular direction do we move for our r distance? Okay, well, let's start actually doing some examples. And the first example I want us to look at is just the function r of theta is equal to 2. So if we went ahead and tried to make our table of theta values, r values, and then the associated r theta values, well, what's a little different here is, well, we know that for every single theta value, even 0, pi over 4, at pi over 2, pi, 2 pi, etc., our r is always equal to 2, no matter what the angle is for this particular example. So let's just go through this process. So, if we're going to plot this particular curve, we plot it on the xy plane, because that's where polar curves live. And we're told, well, at an angle of 0, which means we're right along the x-axis, we're a distance 2 away. Say that's a distance of 2. Okay, let's move to the next angle. Well, in this case, we're at an angle of pi over 4. We're asking ourselves, okay, well, how far do we move along that angle of pi over 4? And, well, we move a distance of 2 as well. Okay, let's move to the next angle. When we're at an angle of pi over 2, we are straight up. And we're asking ourselves, okay, at this particular angle, how far along that direction do I move? And we're told, well, r equals 2 at that particular angle. So we move a distance of 2. And mind you, I'm only really checking off 2 and 2 on the x and y axes because those are easy to count because we typically have the tick marks there. All right, let's keep going. Well, at an angle of pi, which means we are on the negative x-axis, we ask ourselves, how far along that direction do I move? In this case, well, we still move a distance of 2. And you can probably guess, well, at every single angle we could consider, since r is always going to be equal to 2, we are always moving a distance of 2 just away from the origin, no matter what angle we're at. Whether we're at an angle of 7 pi over 4, whether we're at an angle of 3 pi over 2, whether we're at an angle of 5 pi over 4, whether we're at an angle of 3 pi over 4, etc., we're always a distance of 2 from the origin. So if we went ahead and tried to just plot what this curve looks like, well, if r is always equal to 2 no matter what the angle, we are a circle. In particular, a circle of radius 2. All right, the big things I wanted to point out here is, for every single angle, we always ask ourselves, how far do we move in that particular direction? All right, let's do another example. Well, in the last example, we had r was always equal to 2. In this example, let's actually have theta is always equal to pi over 4. Okay, well, let's go ahead and make our table. So we have theta values, we have our r values, we have our r theta values. And, well, we are told that theta, no matter what, it's equal to pi over 4. We're not actually told in this example what r is. For all we know, r could equal 1. R could equal negative 1. R could equal 17. R could equal negative 3.4. We're not told what r is in this case. We're just told we're always at an angle of pi over 4. So let's actually see what that means when we go ahead and plot. Well, again, we plot polar curves on the xy plane. So let's move in a direction of pi over 4. Okay? So pi over 4, our angle is pi over 4 off the x-axis. And say we're told, okay, we move a distance of 1 along it. All right. All right, but since r could be anything, it could be 1, it could be 2, it could be 3, it could be 17. So it looks like we're actually just any point along that angle of pi over 4. But remember, we're also told, like I put in this example, r could also be negative. We're not told what r is. And if you remember before, well, negative values of r, those just reflect us over the origin. or essentially we add pi to whatever our angle is. So if our angle was pi over 4, our angle that we reflect to is 5 pi over 4. So we include all of the values in quadrant 3 as well. So this pi over 4 is a line, but it extends both ways in terms of positive r and in terms of negative r values as well. All right, let's do another example. And this example is going to be more of the standard kind of polar curve examples you'll see, not just where r is a specific number or where theta is a specific number, but this is going to be the curve where r of theta is equal to an actual function of theta, say 2 cosine of theta. And we're told that theta in this example is going to run between 0 and pi. So we have kind of the beginning point and the terminal point for our theta values. So let's see what type of shape we get here, or what type of curve I should say. So we can go ahead and make our table. So we'll start off with theta. We have r, and then we have our point r theta. Okay, and this is where knowing your trig identities, or not trig identities, but unit circle trig values is really going to be helpful. So for example here, let's just consider a couple of the unit circle angles to begin. Say theta equals 0, theta equals pi over 6, pi over 4, say pi over 3, and pi over 2. We'll choose a couple more later. Actually, let's just toss them in. Say 2 pi over 3, as well as 3 pi over 4, 5 pi over 6, and pi. Just give us a little more room in that r column. All right. And well, when we're at an angle, make a little more room here. So here's our curve that we'll plot values on. Well, when we're at an angle of 0, 2 times the cosine of 0, that gives us a 2. So this first point that we'll consider is 2 comma 0. And again, remember, we're at an angle of 0, so we're somewhere along the x-axis. And we need to go out a distance of 2. Let's just say that. So that's our first point. All right, next. When theta is equal to pi over 6, our r value is 2 times the cosine of pi over 6. Cosine of pi over 6 is 3 pi over 2, which means r is equal to square root of 3. So at an angle of pi over 6, somewhere like that, our r value is about square root of 3, which we know is, well, smaller than 2, larger than 1. So somewhere maybe around here or so. So again, the way that I'm trying to indicate this is our blue line is that angle, and the red line is how far along that angle we're actually moving. All right, so let's go to pi over 4. R is equal to 2 times the cosine of pi over 4, which in this case, well, that's pi over 2. So we're at a distance of r equals pi over, or sorry, of square root of 2 from the origin at an angle of pi over 4. So let's go ahead and check that now. So at an angle of pi over 4, we're somewhere around here. And, well, if we're a distance of square root of 2 away, square root of 2 is slightly smaller than square root of 3. So at that particular angle, maybe we're somewhere like this. All right, let's keep going. At the angle of pi over 3, well, cosine of pi over 3 is 1/2. So 2 times 1/2, that gives us a 1. So the next point we're at is a 1, comma, pi over 3. So we investigate along that angle of pi over 3, and we have to move out a distance of 1. And, well, 1 is smaller than square root of 2, so we know we're closer to the origin than that point. Again, this is by no means a very good sketch. Okay, so let's keep going. Well, at an angle of pi over 2, cosine of pi over 2 is 0. So r equals 2 times 0, or 0. So our radius is 0 at an angle of pi over 2. And even though our radius is 0, we still ask ourselves the same thing. At that angle of pi over 2, which is straight up, we're moving out a distance of 0 along it. So we're actually just sitting at the origin. All right, let's do a couple more points. At an angle of 2 pi over 3, r is equal to 2 times the cosine of 2 pi over 3, which is a negative 1/2. So 2 times negative 1/2, that gives us a -1. So we're at r equals -1 at an angle of 2 pi over 3. So let's check this out. At an angle of 2 pi over 3, normally, we would be pointed sort of in that direction in the second quadrant. But since r is now negative, we actually point in the opposite direction since r is negative. And only because r is negative. So we go out a distance of 1 in that negative direction. Again, because r is negative, we would normally be along this blue line of 2 pi over 3, but since r is negative, we move the opposite direction across the x or across the origin, and we move out a distance of 1. Somewhere like that. Okay, well, let's check out the next value. At an angle of 3 pi over 4, r is equal to 2 times the cosine of 3 pi over 4. And, well, the cosine of 3 pi over 4 is square root of 2 over 2. So our r value, or sorry, negative square root of 2 over 2. So our r value here is just a negative square root of 2. So we have to ask ourselves the same thing. At an angle now of 3 pi over 4, normally we'd be extending in sort of that direction in the second quadrant, but because r is negative, we pop over the origin and reflect the opposite way. So instead of going out a distance of square root of 2, sort of in that blue direction in the second quadrant, we're moving out a distance of square root of 2 in that fourth quadrant now. All right, let's keep going. So now at an angle of 5 pi over 6, our r value is 2 times the cosine of 5 pi over 6. Cosine of 5 pi over 6 is a negative square root of 3 over 2. So times 2 for r gives us r is equal to minus square root of 3. So again, we have a negative r value here. This time we're at an angle of 5 pi over 6. So extending out in that direction normally of 5 pi over 6, would place us somewhere in the second quadrant, but because r is negative, we reflect over the origin and go the opposite way. So instead of going out 5 pi over, a distance of square root of 3, sort of in that second quadrant in the blue direction, we're going out a distance of square root of 3 in the fourth quadrant in that purple direction. All right, and let's consider this final angle for pi. Remember, we're just going between theta values of 0 and pi in this example. So in this last value of pi, r is equal to 2 times the cosine of pi, which gives us a minus 2. So r here is again negative. It's negative 2 now. We're at an angle of, well, pi. So let's consider that again. At an angle of pi, well, that is in the negative x direction. But because r is negative, we reflect over the origin and go towards the positive x direction in this case. So instead of going to a distance of 2 in the pi direction, because r is negative, we go over a distance of 2 in that purple direction in the positive x direction. And when we do that, lo and behold, we actually overlap with the first point that we plotted. So if we go ahead and just connect all of these points, this is our polar curve. Oops. And if I was a better artist, this curve actually gives us a circle. Now, we haven't shown that it's actually a circle, and just by this crude sketch I made, it's not very obvious it's a circle, but we could actually go ahead and try to prove that this is a circle by going from r and theta coordinates into Cartesian coordinates by using our translation equations. The big things I want us to take away here is we're able to plot polar curves in the way we would plot any curve just by going point to point. We choose an independent variable. Here, our independent variable is theta. And for every theta value, we just get an associated r value along with it. And we go point by point at a specific angle. How far out do we move in that direction? And that is the distance r. And when r is negative, we have to do that business of reflecting over the origin.